Now that we are familiar with data space and how to compute nearest neighbors, we can talk about how data points might be grouped together in the space. Today, we will talk about how to find groups or clusters of data points. Hi, I am Dr. Shahriar Hussain. You are watching one of the videos of the Data Science lecture series on computingforall.com. Let's talk about how to find clusters of data points. Let us start by discussing what is clustering. The task of automatically detecting neighborhoods or groups of data points is called clustering. Clustering is an analytic approach to check if some points are grouped together in the data, forming a neighborhood. Being able to detect such neighborhoods or groups of points helps data scientists determine objects that have similar properties. If we write an algorithm to find clusters, what should be the input and the output of that algorithm? A clustering algorithm takes the data points or a dataset as input. Sometimes additional inputs are required depending on how the algorithm is designed to find the clusters. We will discuss specific clustering algorithms in the upcoming lessons, where we will see that data is the common input for any clustering algorithm, but there are other parameters too. For now, let us remember that the entire dataset is an input for any clustering algorithm. Now, what is the output of a clustering algorithm? A clustering algorithm outputs several clusters, each composed of a subset of the data points provided in the data. Let us start with a simple example like this one. We have this two-dimensional data set. That means we can compute the distance between any pair of objects or rows of this data set. The distance measure is the basis of any clustering algorithm. We already know how to compute the distance between two rows or two data points using a distance measure like Euclidean distance or Manhattan distance. Before we dive into the details of any clustering algorithm, let us discuss more on the clustering problem. Our data has two features here, or two dimensions. That means we can draw a two-dimensional plot to see how the points look like in the space. Here are the data points in the two-dimensional space. Now that we have a visual representation of the data, can we see how many groups of points are there? There are actually two groups. One group is in the lower left side and the other group is in the upper right side. The lower left group has 4 data points and the upper right group has 5 data points. Let us call the lower left group cluster 1 and let us call the upper right group cluster 2. Given the data points and the plot, can we fill out an array with cluster IDs such as cluster 1 and cluster 2 to represent assigned clusters for each row? So let us draw that array here. So we have a total of 9 rows. For each row, we want to assign a cluster, and from the figure, we can see that 9, 11 is here. That means it is in cluster 2. 11, 13 is here. That is, it is also in cluster 2. 5, 4, this row is here and hence it is in cluster 1. 3, 4 is here. It is in cluster 1. 10, 12 is here, which is in cluster 2. 2, 5 is right here, and it is in cluster 1. 12, 12 is this point. Therefore, it is in cluster 2. 11, 14 is in cluster 2. Then 1, 3, this point is right here, which is in cluster 1. The outcome of a clustering algorithm is this particular array. This array is called an assignment array or cluster assignment vector. The cluster assignment array or the cluster assignment vector provides the cluster ID of each row of the dataset. Hence, this assignment array will have equal number of cells as the data set. In this dataset, we have 9 rows, and hence we have 9 cells in the assignment array. Therefore, the purpose of any clustering algorithm is to fill out an array that has a number of cells equal to number of rows in the data. For any dimensional data, the clustering algorithm must output which cluster each row of the data belongs to. Now, what is the basis of any clustering algorithm? The basic clustering objective is to construct clusters of data points with low intra-cluster distance and high inter-cluster distance. Intra-cluster distance refers to the distance between pairs of points in the same cluster. So if you have points like this in a cluster, then the distance between pairs of objects within this cluster would be called intra-cluster distance. You might have another cluster. The intra-cluster distance inside this cluster would be represented by pairwise distances of all the points you have in this cluster. We expect that a clustering algorithm will provide low intra-cluster distance. That means the points within the cluster should be very close to one another so that these distances are very small. That means we expect that the clusters or the points inside the cluster would be very similar with low distance, and they should be very local, very compact. At the same time, we expect that the clusters would exhibit high intercluster distance. Intercluster distance refers to the distance between pairs of points across different clusters. Intercluster distance is if we take a pair of points whose one endpoint is in one cluster and another endpoint is in another cluster. This would refer to an intercluster distance. Basically, our target is to make sure that points in these two separate clusters are as far as possible. So we want these clusters to be well separated, and that is reflected through this particular objective, high intercluster distance. The overall clustering objective is to create tight neighborhood of clusters of points, and at the same time clusters should be separated as much as possible. In a good clustering outcome, the data points in the same cluster are highly similar. That is, data points in the same cluster have lower distance. Along with that, data points in different clusters are highly dissimilar. That is, points of different clusters should have high distance. Again, a good clustering provides low intra-cluster distance and high inter-cluster distance. What are the analytical benefits of clustering data points? Suppose a data scientist receives a dataset with millions of rows and tons of dimensions. It is hard to analyze the data without some domain knowledge. Since a data scientist or analyst might not have the domain knowledge to start synthesizing the data, she or he looks to the structure of the data by clustering it. That is, clustering gives you the structure within the data. There might be data points with similar properties that might be of interest to the client. Clustering brings similar objects or rows in the same group. That is, clustering is an abstraction of the data. It is easy to start from 5 clusters compared to directly analyze 1 million data points. Clustering is a mechanism to explore data when there is not much information regarding the data or when a specific data analytic problem is not provided. Therefore, clustering is an exploratory analytic task. In the literature, there are several types of clustering algorithms, but most clustering algorithms fall under 3 categories. One is partitional clustering, the second one is hierarchical clustering, and the third one is density-based clustering. Let us talk about each of these types of clustering algorithms briefly. In the upcoming lessons, we will talk about specific algorithms in each of these types. Let's start with partitional clustering algorithm. Partitional clustering algorithm attempts to partition the mathematical space of the data into k divisions, forming k clusters. On this figure, basically we clustered or divided the space into 3 parts using these dashed lines. The figure shows 3 partitions formed in a 2-dimensional space representing a 2-dimensional dataset. The points in each of the partitions form a cluster. Partitional clustering algorithms deal with the data space and focus on creating a certain number of divisions of the space. The most popular partitional clustering algorithm, and probably the most used clustering algorithm in the history of humankind, is the k-means clustering algorithm, which is a topic of a future lesson. A limitation of a partitional clustering algorithm is that an explicit vector space is required for the clustering algorithm. That means an explicit mathematical space has to be provided. That means the actual data table must be provided where you have the numerical values in the data table. If we plan to cluster tweets or short strings, a partitional clustering algorithm is not a good choice because we cannot create the mathematical space for small messages. If we can create a mathematical space, then we can use k-means clustering algorithm. A partitional clustering algorithm goes well with numerical data and not so well with string or text data unless the string or text datasets are converted to tabular data. Conversion of text datasets or document collections to tabular dataset is a topic of a future lesson. Now let us talk about the second type of clustering algorithm, which is hierarchical clustering. Hierarchical clustering constructs A hierarchy representation of how clusters of objects can be developed gradually either by merging clusters starting from many or by splitting clusters starting from one. The approach that merges clusters gradually to form a large cluster is called an agglomerative approach. The approach that splits clusters in each iteration is called a divisive approach or a top-down approach. The agglomerative approach is more commonly used by practitioners compared to the divisive approach. We will discuss a standard hierarchical agglomerative clustering algorithm later in a future lesson. For now, let's say that we have some data points like this. Hierarchical agglomerative clustering algorithm will consider that each of these points is a cluster in the very beginning. Then it will start by merging the closest pair. Let's say that this is the closest pair. Now this pair will be considered as one point. Then the next closest pair will be merged. So let's say that this and this group of points have the least amount of distance. So these 3 points will be merged together. In the next iteration, maybe this point is the closest one to this one, and as a result, these 2 points are merged. Maybe later these 2 points are merged, so and so forth. At some point in the very final stage, all these points will be in one cluster. In the way, notice that in the very bottom level of a tree, if we consider that we have the points, these points will keep merging, creating a branch, and that's why this is called hierarchical agglomerative clustering. Again, we will talk about a hierarchical agglomerative clustering algorithm in a future lesson. Let's talk about the third kind of clustering algorithm, which is commonly known as density-based clustering algorithms. A density-based clustering algorithm can generate arbitrary shaped clusters. Density-based clustering algorithms are used when data points in the space form dense regions. A distribution where most points surround a particular mean and the density of the points reduces as they drift from the mean is called a normal distribution. Partitional clustering algorithm works best for normal distribution, and density-based clustering algorithm works better for these sorts of arbitrary shapes. In this figure, we have three clusters, and these three clusters are actually formed via the density. Notice that the partitional clustering algorithm would try to create partitions, which is not possible for this particular arrangement of the points. dbScan is more appropriate because it works with dense regions, or it works with the density connected regions. If we have points in the space forming these sorts of structure, and if we have another group of points here, if we apply density-based clustering algorithm, the algorithm will be able to detect two dense regions, one here and the other one here. But if we apply partitional clustering algorithm, then maybe these points here will be considered one cluster and these points here will be considered another cluster. Any other partition will not be able to separate these two clusters. In another sense, we can say that density-based clustering algorithm works with non-convex groups or non-convex structures, whereas Partitional clustering algorithm works with convex shapes. Now, what do we mean by convex and non-convex shapes? Basically, let's say that we have a shape like this one. Let's consider that this is a polygon. This shape is convex. The definition of convex is if you go from one corner to another corner, then if you keep going to the same direction, basically you are turning left here. From here you are turning left here. From here you are turning left here. From here you are turning left. So basically every time you reach a corner you are turning left whenever you are going to traverse the corners. This is called convex. Okay, this is called convex. Now in a non-convex polygon, let's say this one, from here, from this particular point, if we go here, we turn left, but notice that from this particular point we turn right. From here we turn left. 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 But there was one point here, one corner here from which we turned right. So if you keep going in one direction, you will be always going to left, or if you go in another direction, you will be always going to right if you have a convex structure. In a non-convex structure, you will change your direction. You will not always be going to the left, or you will not be always going to the right. This is called non-convex and this is called convex. When you can create a circle or a polygon structure to hold your data or to hold a cluster, then this dataset is suitable for partitional clustering. So this is a two-dimensional dataset, so you'll be able to hold them within a circle. If you had a three-dimensional dataset, you will be able to hold the points within a sphere. If you have more than 3 dimensions, you will be able to hold the points within a hypersphere. And a sphere or a circle is convex. But when we talk about this source of structure, notice that we are not always going to just one side. From here we are turning left, but you will notice that from here we are turning to the right side. So basically from one point to another point here within the same cluster, if we draw a line, we'll see that the line is out of the region that holds the cluster. When we talk about convex shapes like this one, if you draw a line between 2 points, that entire line will be within that circle that we are talking about when we talk about partitional clustering algorithm. So basically, if you think that your datasets have non-convex shapes, then you would prefer to apply density-based clustering algorithms. When you think that your dataset has points like this which can be kept within a convex polygon or within a convex shape like a circle or a sphere, then you should apply partitional clustering algorithm. You'll be surprised to find that many datasets actually will support partitional clustering because natural datasets have points around a mean point. So that means you will see that many of the points are very close to a center or to a mean point or average point. There are lesser points that are far away from this center. These sorts of patterns help us analyze data. If we did not have any pattern in the data, then we could not apply these sorts of clustering algorithm. As I said earlier, clustering is an exploratory analytic tool. That means that you apply clustering to figure out if there are structures in your dataset, because a structure or groups would mean that there are objects that share common properties, and those common properties might be of interest to the client. Now that we know the basics of clustering, we will move forward with the algorithms and corresponding Python codes in the coming lessons. I hope you found this video informative. If you enjoyed the video, subscribe to this channel so that you receive a notification when we publish any new video. Wish you a wonderful time.